In this video, I'm going to show you how to calculate limits of rational functions by factoring. So here we want to compute the following limit, the limit as x approaches 0 of the rational function x squared plus x over x squared plus 2x. Of course, the easiest way to compute a limit is just to use direct substitution, so that should always be our first attempt when we're doing a limit. So why don't we try it here? Let's try direct substitution. If we attempt direct substitution and we just sub in that value 0 for x, we get 0 squared plus 0 over 0 squared plus 2 times 0, which evaluates to just 0 over 0. And this is called indeterminate form. And the reason why it's called that is because we're unable to determine the actual value of the limit from this form. 0 over 0 could be 0 or infinity or any other number. This limit evaluates to something, but 0 over 0 doesn't tell us what that something is. So we have a little problem here. When we do direct substitution, we still can't tell what the limit evaluates to. Now for rational expressions, there's a way to remedy this problem. We can just factor the numerator and denominator and simplify. So let's write that down here. Factor and simplify. So why don't we go ahead and try that? So we have the limit as x approaches 0 of the numerator x squared plus x over the denominator x squared plus 2x. And we see that we can factor out an x from both the numerator and the denominator. So the numerator will become x times the quantity x plus 1, and the denominator will become x times the quantity x plus 2. So we can go ahead and cancel out these x's. So this is just the limit as x approaches 0 of x plus 1 over x plus 2. And now we can go ahead and attempt direct substitution again using the simplified form of the limit. So limit as x approaches 0 of x plus 1 over x plus 2, and then we'll go ahead and plug in 0 for x. So 0 plus 1 over 0 plus 2, and that just comes out to a half. So there we go. That's it. The limit is equal to a half. Here's another problem for us. We want to compute the following limit. The limit as x approaches 1 of x squared plus 2x minus 3 over x squared minus 1. And again, why don't we go ahead and start off trying direct substitution. If we do that, then we take limit as x approaches 1, x squared plus 2x minus 3 over x squared minus 1. If we plug in 1 for x there, we get 1 squared plus 2 times 1 minus 3 over 1 squared minus 1. Go ahead and simplify that. 1 plus 2 minus 3 over 1 minus 1, which is just 0 over 0. So again, we have indeterminate form, and we need to figure out some way to simplify the limit so that we can actually see what the value is. The indeterminate form doesn't make it clear to us. So why don't we go ahead and apply the same strategy of factoring and then simplifying. So if we factor and simplify, then we have that the limit as x approaches 1 of x squared plus 2x minus 3 over x squared minus 1 is equal to the same limit, but factor the numerator and denominator. The numerator factors into x plus 3 times x minus 1, and the denominator factors into x plus 1 times x minus 1. And we see that x minus 1 can cancel in the numerator and denominator. So this is just the limit as x approaches 1 of x plus 3 over x plus 1. Alright, so now we've simplified the limit a bunch. Let's go ahead and try direct substitution again now that we've simplified the limit. So it becomes the limit as x approaches 1 of x plus 3 over x plus 1, and we just substitute in x equals 1 there, so 1 plus 3 over 1 plus 1, which is equal to 4 over 2, which is 2. So there we go. We have a sensible answer now. 2 is the value of the limit. Alright, another problem. We want to compute the following limit as x approaches 0 of 1 over x minus 2 over x squared plus 2x. As usual, we'll begin by just trying direct substitution. And when we try direct substitution on that limit, we plug in 0 for x, and we get 1 over 0 minus 2 over 0 squared plus 2 times 0. So really we have 1 over 0 minus 2 over 0. Okay, and again, that's not really helpful because 1 over 0 isn't defined, and neither is 2 over 0. These could represent positive or negative infinities, and subtracting infinities from each other isn't defined. So this is indeterminate form as well. Now this one's a little bit trickier because to overcome indeterminate form in previous examples, we've just gone ahead and factored the numerator and denominator of the rational function. But this rational function is actually split up into two parts. It's one fraction minus another fraction. So what do we do here? Well, one way to get around the problem is to force this limit to take the form of a single rational function. So why don't we do that? Why don't we combine the fractions? So we'll go ahead and combine the fractions. We'll have that limit as x approaches 0 of 1 over x minus 2 over x squared plus 2x is equal to limit as x approaches 0 of the following. Let's go ahead and factor the denominators first. So we'll have 1 over x, that just stays as is. This minus 2 over x squared plus 2x can be factored into x times x plus 2. Now to combine the fractions, we need to have them have a common denominator. And we see that the factor of x is already included in the second fraction's denominator, but the first fraction needs a denominator of x plus 2. So let's go ahead and multiply it by x plus 2 over x plus 2 in the first fraction. We get that. Okay, so now the fractions have the same denominator, x times x plus 2, and we can go ahead and subtract them. So let's just continue this work over here. So that becomes limit as x approaches 0 of x plus 2 minus 2 is just x. So x over x times x plus 2. And hey, something pops out to us immediately. We have an x up top and an x in the denominator. So we can go ahead and cancel both of these x's, and this just becomes the limit as x goes to 0 of 1 over x plus 2. So we really did two steps here. We not only combined fractions, and we also simplified. The factoring was kind of implicit. It just kind of popped out as we were combining the fractions. Okay, so nevertheless, we have our limit in a lot better form now, and we're ready to go ahead and try direct substitution. Again, let's give it another shot. This time it should work out nicely. So limit as x approaches 0 of 1 over x plus 2, and we go ahead and substitute in 0 for x there. So that's equal to 1 over 0 plus 2, which is just 1 over 2, a half. So there we go. We've got a nice, sensible result. All we did was simplify the limit a little bit. We didn't change its actual value, so 1/2 is indeed the value of the limit. So there we go. Now we know how to calculate limits of rational functions by factoring. In the future, we'll also learn tricks to deal with even more complicated limits, such as limits involving roots.